Welcome back, scholars. This video will be the first in a series of refresher lessons concerning all things functions. Whether you're heading to AP Calculus AB or BC, you'll find that the concepts that we look over the next several videos will be foundational to your success as you start building on your algebra concepts in the future. Let's get started. A great place to start talking about functions is, of course, the definition of a function. In the past, you learned that a function is a pairing or a correspondence between two sets of numbers. The pairing goes from the first set, called the domain or inputs, to the second set, called the range or the outputs. When we say the phrase function, we're talking about a special type of relation where every input maps to one and only one output. I like to think of this like a restaurant menu. Every item on the menu can have just one price at any given time. However, the same price may show up more than once. We'll see that idea on the left here with this quadratic function. Notice that the same set of outputs repeats on the left and right-hand sides. However, for every individual input, there is only one output associated with it. It's convenient to use a combination of tables, graphs, and equations to represent functions. If we use a graph, we'll need to define the axes. Here I've used the input axis, also called the independent variable, on the horizontal axis labeled x. On the vertical axis, I've shown the outputs or dependent variables labeled y. The equation representing the graph shown here is y equals x squared. In this case, we can say that y is a function of x. If we glance over to the right-hand side, we see the same conic section, a parabola, however, it's been rotated 90 degrees relative to the parabola on the left. Note that my axes have the same labels. However, unlike the green parabola, this parabola shown to the right pairs two different outputs associated with the same input labeled a. The equation x equals y squared applies here. In this case, y is not a function of x, which we can show or prove using the graph. You'll commonly hear that this is not a function, but strictly speaking, that statement is not true or false, it's just incomplete. We can't describe a function without also describing the pairing. So it is true that y is not a function of x in the case of the parabola opening to the right. However, it is true that x is a function of y. That would require that we define the inputs as y and the outputs as x. Let's talk real quick about function notation. As you continue further in your mathematical careers, it will become more and more important that you can communicate with and understand both written and verbal symbolic language. You're already familiar with function notation such as f of x. We read this out loud as f evaluated at the input x, or frequently it's just read in shorthand as f of x. This notation holds a lot of hidden meaning. It implies that the output, usually y, corresponds to a particular input, which is shown in parentheses, in this case x. But be careful, this notation does not mean multiplication. For example, this is not the variable f multiplied by the variable x. In the table, you'll see some of the common symbols we use with functions and their meanings. For instance, when we refer to the function, we are speaking about the relationship between the two variables, which could be described by a graph, equation, etc. When we say x, we're generally referring to the input, but the input could formally be any variable letter, not just x. And as we saw when we studied vectors, the input is also referred to as the argument of a function. When you see the notation f of x, this is standing in to represent the output, which is often y. You should be able to see and use those phrases interchangeably. One of the simplest tasks we can perform with functions is to evaluate a function at a particular input. This can be done using any of its representations, a graph, a table, or an equation. Let's use f of x equals the absolute value of x minus 2, which is also shown over here on the right. The notation f of 0 means the value of the function at the input 0. Using the graph or using the equation, we can see that that will be 2. F of 8, or f at 8, means the value of the function at the input 8. Well, the graph doesn't show that, so let's use the equation. We'll replace the placeholder x with the input that we want to evaluate, so this will be the absolute value of 8 minus 2, which is of course 6. Finally, we can work backward from the output to determine what input or inputs map to that output. The notation f of x equals 2 is saying what inputs produce the output or y value of 2. From the graph, we can see that this is likely to be 2 inputs. I can see that the function is equal to 2 at 2 unique inputs, at x equals 0 and at x equals 4. We can also use the equation to find those values. Since this is an absolute value function, we'll set the expression, the absolute value of x minus 2 equal to the desired output, which is 2. Now, we'll get an absolute value of 2 whether x minus 2 is positive 2 or negative 2. So that's why we have two different equations, and subsequently two different values of x for this output. Note that this is still a function because each input is still paired to only one output. Remember, we can reuse the same outputs. What about this last one, f of a plus 2? Well, this notation is saying that we'll replace the input x with the entire expression a plus 2. So the absolute value of x minus 2 will be the absolute value of a plus 2 minus 2, or simplified, just the absolute value of a. Let's dive into a really important concept for calculus, which is the average rate of change. Now, when you first started studying algebra, the first function that you learned was the linear function, which has a defining feature, a constant rate of change, which we call its slope. Of course, as you learned more complicated functions, we saw that for the most part, functions do not have a constant rate of change. So we can't calculate slope per se, but we can estimate between 2 points. We'll do this by looking at the change in output compared to the change in input over those two given points. In the sciences, you see this delta notation used extensively. The Greek letter delta is often used as a shorthand way of representing the phrase change. So we have the change in y divided by the change in x. Using function notation, this is the difference in the output at x2 and x1. Now, we can only calculate the average rate of change if we're given a starting and an ending point. We can visualize this process geometrically by thinking of the average rate of change as a linear approximation through those 2 points. In the image, we have a function given by the nonlinear curve in black. Suppose we have two given points, P and Q. We can draw a straight line through those 2 points, and the slope of that line would be the average rate of change over the interval PQ. Now let's jump over to Desmos for just a moment so I can demonstrate an interesting idea. Here's a picture that looks similar to the image from our notes. We have our blue secant line and we have our 2 points. We'll call them P and Q. Notice that as the points get further apart, the slope of the secant line becomes a poorer representation of what's happening in the middle of the function. But it's a good approximation of the long-term change. On the other hand, as the points get closer and closer together, the secant line starts to inch closer and closer to becoming what is called a tangent line. That is, a line that touches the curve at exactly 1 point. In fact, the average rate of change in this case becomes a better and better approximation of the rate of change at that exact point or moment in the function. This concept is what we call the instantaneous rate of change and is the basis of the derivative, which is a cornerstone of calculus. Looking back at our image, I want to point out just one more thing. You'll see that this triangle model that we've been using throughout pre-calculus shows up time and time again. Be careful in understanding that the average rate of change from P to Q is the ratio of y over x, while the distance between P and Q is given by the Pythagorean theorem. Let's practice finding the average rate of change for a quartic function, f of x equals x to the fourth, for 3 different intervals. Starting over here on the left, we have the interval from x equals -1 to x equals 0. We can use the equation or the graph to evaluate the function at each of these inputs. We can see that the secant line drawn through these 2 points has a negative slope, so the average rate of change will be negative. The change in y is -1, and the change in x is +1 over that interval. So the slope of the secant line and the average rate of change is -1. Note that the average rate of change is not constant over the function. In the middle, the secant line has a slope of +1. On the far right, over the interval from x equals 1 to x equals 2, the average rate of change is +16. Now that we understand the average rate of change concept, let's think about what would happen if we wanted to calculate the average rate of change over an interval, but we didn't know the exact starting or ending point. We instead just knew how far apart the 2 points are. This idea is represented by the difference quotient. Written in this form, we calculate the average rate of change from the point x to the point x plus h. We assume that x and x plus h are not equal to one another, so h is not equal to 0. And in general, h is the difference between the 2 inputs or the points x1 and x2. Again, the difference quotient is how we calculate the average rate of change if we know how far apart the 2 points are, but not necessarily the precise starting or ending point. So we're generalizing our inputs as x and x plus h instead of saying something like from x equals 0 to x equals 1. It's essential that you're able to calculate the difference quotient algebraically, and it's very easy to do. Let's do one together. The instructions say calculate the difference quotient for f of x equals 2x squared plus 1. And what we're going to do is use this template or formula to find the 2 pieces in the numerator. Let's start with the first term, f of x plus h. Just as we did before, we're going to replace the input placeholder x in our function with the entire expression x plus h. So this will be 2 times x plus h quantity squared plus 1. We'll need to expand the binomial x plus h times x plus h. Then distribute the factor 2 into the trinomial. There are no like terms to combine, so we'll stop there. The second term in the numerator is just the function rule itself, f of x. So we'll go ahead and find the difference, which means that we'll subtract the first and second terms, f of x plus h minus f of x. Now be careful, you need to remember to apply the subtraction to both the 2x squared term and the plus 1 term. Then combine your like terms. So our numerator will be 4xh plus 2h squared, and this will sit above our denominator, which is h. The last thing we'll check for is a common factor of h in our numerator terms. Since I have addition between my 2 terms in the numerator, the division applies to both terms. So I'll break my fraction up to show that. Alright, we can see that common factor of h very easily now. I'll reduce h over h to just 1, and that leaves a final expression of 2x plus 2h, where h is not equal to 0 based on our initial conditions. That was quite a lot for one video, but hopefully many of these concepts were already familiar to you. Next time we'll pick up with domain and range, as well as operations with and compositions of functions. We'll see you then.